Yeah, good morning, everyone. Let's start off. Which one you can? So this was the last thing that we did, smooth bank road. If you see last class, we were discussing why you need to bank the roads. What happens if you make a curved road, which is horizontal. So now let's see the second part, what happens if there is a friction and also it is banked. Everyone should keep the cams on. So this is theta. We have a vehicle. This is the circle of radius r and this is mu. Copy it down. Mu is the coefficient of friction. Now let's see what happens exactly. So imagine if you're going very fast, what will happen? You're going so fast, the vehicle will start skidding outside. If you're going too slow, the vehicle might slide down. So we have to consider both the cases. So let's see what will happen. Put it up. Turning the page. Let's see. For maximum speed. Let's say the vehicle is going very fast. So what will happen? Vehicle will tend to slide outside. Meaning, imagine when you're going very fast on a road, how do you skid? You'll skid away from the road, na? You'll go and hit the divider though. You're skidding outside. So when you draw the FBD, this is how it looks. Normal reaction, your own weight. Since you're skidding outside, friction is inside like this, down. And इसके ऊपर there is a centrifugal force. Now remember, the moment you use the centrifugal force, where is the observer? Observer is sitting on the car. That's the important thing. Like, you should know, like, when you're using centrifugal force, just have an understanding. Okay, my observer is on the car. If you use centripetal acceleration, where is the observer? On the ground. So that is the major thing. So then if I try to resolve the forces, see what do I get? Normal reaction, mg cos theta, this stuff, mg sin theta. Now the pseudo force is also there, no? mv square by r, this was theta r. Yeah. Someone said something. So this is mv square by r sin theta. This component will be mv square by r cos theta. Any doubt on this division of components? Ask me here. Centrifugal force also you are dividing along the normal and perpendicular to the incline. So if you take those components, mv square by r cos theta and mv square by r sin theta. So we have to track the centrifugal force components also. Till now we never used to take because it was never existed. Balance the forces. So here basically what you did, you took this as your x-axis and this is your y-axis. Now balance the forces. N will be mg cos theta plus mv square by r sin theta. Better see the derivation properly. It is there in 12th ka first chapter in HSC. And it is there. This is the derivation for that. And along the incline, mv square by r cos theta is mg sin theta. Friction is also there. And the friction is maximum because you're on the verge of slipping. So this is equation 1 and this is equation 2. And I also know what is F max, mu into n. So just don't say every time n is mg cos theta. See the question properly. Don't say n is mg cos theta. Don't by heart just randomly like that. Always see, is it relevant what you're speaking, and then check the FBD and then solve for it. Put it on, I'll solve in the next page. Copied. Next thing, let me solve it. So substitute then in the so this will be mb square by r cos theta. Bring all these to one side. This is your maximum speed. You can remove the cos theta common. You get tan theta, and this is 1 minus mu tan theta. This is the maximum speed. Yeah. So if you go anything faster than this, you're going to skid outside. So like last time I was telling you, remember, if you have a rough banked road, you know, you not only get a good speed limit, but you actually get a safety factor also. Now the friction here becomes a additional safety. So on a road, when it is written, speed limit is 40. Even if you go at 50, you don't slip. That is because the friction will come and balance, give that extra force which is required. So instead of getting a single value, you know, which you should go, you get actually a range. So this is the maximum speed of the vehicle. If you go anything faster than this, you're going to slip outside. Put it up. Copy. Then Next thing. So just like a maximum speed, now there is a minimum speed also. Now what happens to the minimum speed? Now you're going so slow, the car will slide downward. Now when you draw the FBT, what are the forces? Normal reaction, friction will be up, mg will be down. The centrifugal force will be away from the center. If you see, I'm drawing it with a different color or a dotted line. It's a centrifugal force. It doesn't exist. Only for problem solving we can use. So when I resolve this into forces, if you observe, the normal reaction won't change. The only thing is friction will be up. Normal reaction and figure out everything is same. Only this F ka direction changed. Then writing the equations, and will be mg cos theta. And I know F is equal to N. If I substitute that, we end up with mv square by r cos theta plus mu. Bring all these to one side, and m got cancelled. This is your minimum speed. You can't be anything slower than this. So you'll get a speed limit, which is v less than v max and less than v minimum. So this will be v less than rg This is the maximum speed. This is the minimum speed. This is the speed limit. But in general, v minimum, right, is kept as 0. Obviously, if you're going on a road and for some reason you stop the road, stop the car, you don't want the car to slide downward. So that's the speed limit. So in case if you have a banked road with a friction, you get a speed limit. Put it up. Copied. Put down the result also. This is the final result which you need to mug up actually. Clear? Next thing.
Can you go to the previous page? Done.
Next thing. Bending of a cyclist. You must have seen this thing, right? Let's say your street which is there near the house that doesn't have any banking or something. Because banking end of the day, right, is expensive. If you're making the road at a bend, you have to use a lot of material and work. So then what you do, if you can just visualize how you go on a cycle, you don't go straight. You will start bending. No? It's like if the road is not banked, you go at an angle in order to balance it out. Why is this happening exactly? If you look at the forces on the man, circle, there is a centrifugal force, mv square by r, and there is an mg. So I just extended this. And this is going in a circle there. So if you take this angle to be theta, we get tan theta is equal to opposite side mv square by r by mg. You end up with v square by rg. Can you see something? This is same as this speed. Banked speed. Meaning, it's like, you know what? If the road is not bent, you are bending in order to compensate for that. At least the answer looks like that. So the angle which you bend while taking a turn is this thing. You must have seen, right? This bike racing and all, people literally feels like they're touching the floor. The reason is the speed is high, the angle also will be more. So in order to compensate for that, it works out that way. So here, basically what is happening, there is something called torque. We will discuss that more in another chapter. So torque due to mg and centrifugal force cancels out. Put this down. So basically mg here is there just trying to make you fall. The centrifugal force is there, it is trying to make you keep you balanced. So both are balancing out. Copied. Next thing.
So wait.
Copied. Next one. Let's see a question. We got a valley, circle of radius r. There is a vehicle going with speed u. It's going up the hill. So it's a convex road. Radius r mass and it's going with speed u. So this is at the lowest position. This is at the highest position. Find the normal reaction at this instant. Find the normal reaction on the block. First thing, free body diagram, then equations and solve. Easy only. See, I'll just tell you here. Here, if you draw the free body diagram, what are the forces? N, mg. Since you're going in a circle, there is a centripetal acceleration. Now, where is the observer? He's on the ground. If you use centripetal acceleration, the observer is on the ground. Then Newton's second law, N minus mg is mac. We get normal reaction is mg plus mu square by r. Similarly, here if you draw the FBD, N mg, since you're going in a circle, acceleration is towards the center. So whenever you go through a valley, the normal reaction increases. When you go up a convex surface, the normal reaction decreases. So when you're going in a roller coaster ride, this is what you experience. The weight is fluctuating, your weight is increasing and decreasing. This is how you solve this in the ground frame. So put this down. Next page, I'll show you how to use centrifugal force also. Now again, centripetal acceleration, centrifugal force. Which one to use? Use whichever is convenient for you. Doesn't matter. But just remember, when you're using centripetal acceleration, you're on the ground. When you use centrifugal force, you're on the body. And don't use both at the same time. As long as you remember this, it doesn't matter which one you use. Next page. So if I do this using, centrifugal force, this is what I observe. N mg, the centrifugal force is away from the center. So in this case, my observer is sitting inside the vehicle. And if you ask him what is the acceleration of the vehicle, he will say acceleration of the car or the block is 0. He said, I'm sitting inside, it doesn't move only. So he will write N minus mg minus mv square by r is mass into acceleration of the car, which was 0. End of the day, you get the same answer. So the only difference is where you are standing. There. So if you see the answer is same, only depends on how you're looking at it. I wrote reverse kya? Mg minus mv square by r. Next thing. Turn in the page. We have a spring. Mass M. Length L. This is a natural length. Spring constant is K. The whole setup is rotating with omega. So particle M is attached to a spring. The other end is fixed. To axis and rotated with omega as shown. This is on a smooth table, okay? So when you're rotating, what will happen? Spring will stretch now. Did you ever observe? If you take a rubber band and tie it to something, and if you rotate it, what will happen? Rubber band will stretch. So find elongation in the spring. So when you're rotating it, find the elongation in the spring. In steady state. Steady state meaning there is no oscillations, nothing. System has reached, elongation has become constant. You can neglect gravity. So anyway, this is on a smooth table, so it won't matter. So basically this guy is going like this. Again, you have a spring, one side you connect it to a hinge vertical axis, and the other side is a particle, you rotate the whole setup with omega. How much will the spring stretch? Any doubts in the question, please ask me. Question is clear, go ahead, I'll give you 2 minutes. See, first thing, free body diagram. So let the elongation be x. So when this guy rotates in a circle, then this length will be L plus x. So this will go in a big circle. It won't go in a circle of L, it will go in a circle of L plus x. So what are the forces on the particle? Centrifugal force, m omega square L plus x. Why am I using m omega square? Because omega is given in the equation. If speed is given, I'll use mu square by r. and the spring force. So if the spring is stretched by x, how much force will it exert? Kx, no? It will be balanced. Where is observer? Observer is standing on this. So Kx is m omega square L plus x. Take out x common. You get m omega square L by k minus m omega square. Easy one. Single step actually should draw the FBD. Single equation, it will get the answer. There's nothing hi-fi here. Have a look at here. The main thing you need to realize is the circle car radius will not be L. It will be L plus x. Because the spring stretched by x, na? The spring force is balanced in the centrifugal force. Put it up. Any doubts on this thing, ask me. Copy it. Next one. This is a top view. We have a round table. So we have two blocks, mass M1, mass M2. This was a center. This was R1 and this is R2. And this whole setup is rotated with omega. Two blocks M1, M2 connected by a string. Are placed on smooth round table and rotated with omega. You know, this thing is like if you rotate too fast, what will happen? There is a chance that both of them will slide outside. This was the center. The question is find R1 by R2 if the blocks don't slip. Meaning there's a particular value of R1 and R2, no matter what you do, they won't slip. They will rotate with the table. This is the top view. So you see two blocks, both are connected by a string. This point is a center. The center is measured from R1 and R2. So and it started rotating in a omega. So there's a particular value of R1 by R2 where the M1, M2 don't fly away. Hope the question is clear. Try. I'll give it 2-3 minutes. See, when you see from the top view now, this is the free body diagram. What are the forces? Tension, centrifugal force, M1 omega square R1. Tension, centrifugal force, M2 omega square R2. You can clearly see this centrifugal force and this centrifugal force cancelling each other. That's why it's not going away. Make sense? So it's like two people are pulling from both the sides. So here the tension will be M2 omega square R2. Here tension would be M1 omega square R1. Since both the tensions are equal, so you end up with M1 R1 is M2 R2. So we have R1 by R2 is M2 by M1. That's the ratio. So it will be in the bigger the mass, lesser the distance. Suppose same question, if the table has been rough, right? Coefficient of friction is mu. I'm just giving an additional question here. They'll ask you like this: find omega when the blocks will slip. Then what will change in the diagram? This will be the forces. Centrifugal force M1 omega square R1. Centrifugal force M2 omega square R2. Now there will be two frictions, F2, F1. So if they're trying to slip on the right side, frictions will be on the left side. If they're trying to slip on the left side, frictions will be on the right side. And then you get from here N1 omega square R1 is balancing N2 omega square R2 plus F1 plus F2. And we know F1, F2 is mu mg. So bring omega this side. That will be mu m1 plus m2 g. So you end up with omega is root over mu m1 plus m2 g by m1 r1 minus m2 r2. You can put a modulus here because it can happen like this. The bodies are slipping this way, the friction will change direction. So the sign will take care of it. It doesn't matter. So if they're slipping on the left hand side, frictions will come on the other side. So if the surface is having friction, this is how you do. Again, I'll tell you what's the difference between these two. Here, there is no friction. Suppose here, if it is slipping on the right side, there will be two frictions on the left side. So the centrifugal force is balancing this plus two frictions. That's it. Then draw an FBD and write the equations. So if the table is having friction, that's how you do the problem. Put it on, have a look at it. Any doubt, anything you didn't get, please ask me. Copied. Next slide. This is a good one. Next one. Here on top view. So here we have a groove, and here you placed a ball. This is R by 2, and this is R. This is N. Meaning the side view will look like this. So you took a a small knife and made a gap in the disc. Able to visualize how it is? And now you started rotating the whole thing with omega. What will happen? The ball will fly outside, na? Just imagine, na, if you keep a coin on top of a fan ka wing and if you rotate it, what will happen? The coin will fly outside, isn't it? So the same thing here. So find the speed of the ball when it comes out of the groove. So you can say a ball is placed inside a groove. Smooth groove on a table. Smooth groove of a round table. As shown. And rotated with omega. So find the speed of the ball when it comes out. Hope everyone agrees that it's going to come out. The centrifugal force is pulling it out, so moves out. So the question is, what is the speed when it comes out? Try. It's a good one. I'll give you 3 minutes. These questions, right? What we're doing after this 25, 26, and all. These are a little tough. Maybe it's like mains may out of that 25 questions, you might get around 5 to 6 like this. Neat way you might get very less actually, maybe 3 to 4, not much. But you do get questions, of little different levels what you're doing today. Try this thing. I'll give you 3 minutes. See, this is a little different. You have to integrate actually. Now let's say the ball is somewhere here at a distance x. What are the forces acting on the ball? There's only one force, centrifugal force acting away. N and mg will cancel. That is into the plane. So the only force acting is centrifugal force. So m omega square x is mass into acceleration. Gets cancelled. You get acceleration is omega square x. What is this acceleration? It's a radial acceleration, meaning it's going away from the center. So basically it's an acceleration along the radius. So I know A is what? V dv by dx is equal to omega square x. So V dv is equal to omega square x dx. Integral limits. When velocity is 0, where are you? You're at r by 2. You didn't start from 0. You started from r by 2, no? V and the limits are r. You finally came out. So here we get v square by 2 is omega square x square by 2. The limits are from r by 2 to r. 2 will cancel out. R square minus r square by 4. So that will be 3r square omega square by 4. So you end up with v is equal to r omega root 3 by 2. This is the radial speed, meaning this, it will come out with this speed along the radius. This is not the complete answer though. Let's see. In the exam, if they ask you find the speed with respect to the platform, this is the answer. But when I say find the speed, it is always with respect to ground. Have a look at till here. The only force acting on this thing is a centrifugal force, just pulling you out. And it is not constant. Dekho. X is changing, the A is changing. That's why I didn't use V is equal to U plus AT. V square minus U square is 2AS. Since A is changing, you can't use the three formulas. You have to integrate. Again, if you see, it's not a big integration, only x power n. Check out the steps. I'll show you in the next page. Copy. Next thing. How does this thing actually go? See, what we got is a radial speed, meaning when this is flying out now, this is the radial speed we calculated. But remember, when you're flying out, there is also a tangential speed. Because you're going in a circle, when you come out, you also have a tangential speed. Meaning, how this ball was actually going? The ball was initially here, now. Like this. This is the direction of the ball. It doesn't come out actually radial. It will go at an angle. It is spiraling out. This is what you will see actually in the ground frame. You can try this thing. Put a coin on your palm, stretch your palm, and try to rotate. You'll observe the coin won't go out straight. It will go at an angle. The ball will fly at an angle. So what is the speed here? So this is V radial and this is V tangential. So the ball will have both the speeds and both are perpendicular. So V tangential square and V radial square. So it will be R omega root over 1 plus 3 by 4. R omega root 7 by 2. That's your answer. The ball comes out at an angle. It doesn't come out exactly along the groove. Because there's a rotational, tangential speed also. Put it down. Copied. Next thing. Everyone keep your cams on, right? Next thing. A ring of mass m and radius r is rotating with omega. Find the tension in the ring. You can neglect gravity. Meaning if you see the top view now, the whole setup is rotating with omega. So why is there a tension in the ring? If you actually check out the FBD, you'll observe on every particle, there's a centrifugal force pulling the ring outside. Then now you tell me, if someone is catching the ring and pulling it everywhere outside. So this thing causes the tension. Centrifugal force is outwards. This creates the tension. So if you just have a ring and if it is rotating with omega, that thing will have a tension. And if you rotate fast enough, what can happen? It can break also. Put on this, I'll show you this thing. This, the proof for the derivation is literally weird. So let me show you. See, listen to the proof carefully. Yeah? Again, the proof is not that important, but the result is important. And better if you can remember the method, so that will be great. Because this is slightly mathematical. So take a very small piece d theta for this small arc. So this length will be how much? R d theta. Now we know, so the dm is the mass of that arc. Will be how much? That will be m by 2 pi r. This is the mass per unit length, mass by total length into length of that small arc. Meaning, in case you're confused, how did you get this thing? For 2 pi r, mass is m. For r d theta, how much is the mass? Unitary method. Does that make sense? So this will be md theta by 2 pi. Great. Next thing. Now, when you take this small piece here, I'm just drawing big, I'm exaggerating so that easy to understand. These are the forces. Tension, tension. So this is the half angle d theta by 2 and this half angle d theta by 2. So if you look at the angles here, if this is d theta by 2, this will also be d theta by 2. This will be 90 minus d theta by 2. So this will be d theta by 2. Similarly, this is also d theta by 2. Then what are the components? This will be t cos d theta by 2. Vertically downward t sine d theta by 2. This is also t sine d theta by 2. This is also t cos d theta by 2. And the centrifugal force is away from the center, which is dm omega square r. You can clearly see the vertical components are balancing the centrifugal force and the horizontal components are cancelling out. So we get 2 times t sine d theta by 2 is dm omega square r. Now we also know this thing for small angles. You can write sine theta is equal to theta. So remember this thing. This we can do only for very small angles. Theta is less than 5 degrees. So here this will become 2t. Sine d theta by 2 becomes d theta by 2. dm is m d theta by 2 pi omega square r. 2 gets cancelled, d theta gets cancelled. So you get tension is m omega square r by 2 pi. The result is important and method is important because this will come in another 5 chapters. Again, what I did, I'll tell you. I took a very small piece. This is a very small piece. Huh? I'm just showing big for exaggeration, meaning it is so small, it looks like this. You can't even see. I found the mass of that small piece. Then I wrote the forces. There'll be one tension, tension, centrifugal force. So tension of vertical components will balance the centrifugal force. So that is 2t sine d theta by 2 is equal to dm omega square r. For small angle, sine theta is theta. So sine d theta by 2 becomes d theta by 2. So I just substituted there and I substituted this dm ka value here and equated. So if I just write down the result here, t is m omega square r by 2 pi. You can mug up this result. Put it down, have a look at this. Again, the derivation is not important for HSC, it's not there, but the result is important for the entrance perspective. Clear? Next page.
Just exploded.
Oh man, it got pulverized.
Yeah.
Minutes for one.
Yeah. So
One
what I've done here,
Vacuum cleaner in American. So it's the motor and it spins really fast. We've hooked up to the mains and hopefully it's Dyson, so it does about sort of like 80,000 RPM. Dust. Just a little bit of dust. Yeah, we've hooked it up. So we've hooked up this Variac to the Dyson motor so that we can vary the speed and the power gain.
yeah. Okay. All right, go for it. I'll run in there.
Okay, hang on, let me just turn this on.
I'll be like this.
Hold on. Okay, start it up. Oh man!
You can actually see it warping in
Yeah.
in real life.
That was awesome. I jumped.
You jumped.
It's a very high speed camera, you know.
It'll happen
Captures at
eventually.
a rate of 11,000 times slower than normal.
That's the thing when
1100
you're
times slower than
filming at this many frames a second. You the actual moment where something happens takes forever to get to.
Yeah.
Whoa! That was awesome because you saw the actual shape of the CD and the cracks in it were perfectly like the direction the CD was spinning. It was like a spiral effect on the CD, like a turbine.
Did you see where it cracked? It cracked on the edge circumference. What is the tension ka formula? M omega square R by 2 pi means bigger the radius, more the tension. So whenever this thing rotates, the first point where it will crack is the circumference only because the tension is maximum there.
All right. So that was at 62,000 frames a second, shattering. Frame
So
rate.
let's slow down a little more. Just go to like a balloon. And listen to the camera just recorded for 4 seconds. Huh? If you want to watch that 4 seconds ka video, that slow speed camera, it takes you 7.5 hours. The file ka size is 96 gigabytes. The 4 seconds ka video is 96 GB file. So high speed camera, right, costs you around 80 to 90 lakhs. There is one in IIT Bombay. They use it for some experiments, but look at these people are just using it to play videos and stuff. Again, the Discovery Channel ka one of the
Shot
program.
96 gigs.
Promotion guys, sir.
In
Shatters.
like a little.
Oh, look at that.
That's awesome.
Just the shape it makes when it shatters.
Like a little tree. Wow, that's cool.
That is amazing.
That's wicked.
That is amazing.
It goes
Yeah,
like
if
either
you
side.
do something
of the
fast enough, you can track it. Good enough. One second. I think my audio got disconnected, I guess. And there is this problem with this YouTube. Like, I don't know. I need to do something about it. Copied. Next page. So those are some of the problems based on uniform circular motion. Next thing is non-uniform circular motion. So what is this non-uniform circular motion? In non-uniform circular motion, the speed is variable. Meaning, if you remember in the circular motion, the speed was constant. So here the speed is variable. Therefore, there is an acceleration. Therefore, there are two acceleration components on the particle. Put it up. There are two acceleration components for the particle. So there is a tangential acceleration. This is responsible for changing speed. So there is no tangential acceleration in uniform circular motion because there the speed was constant, no? And then we had centripetal acceleration. This we studied. So this is required to make you go in a circle. Responsible for particle to go in a circle. So if someone asks you what is a net acceleration, you will say root over a tangential square plus a centripetal square. So in case if a particle is going in a circle with changing speed, then you will have two accelerations. Unlike one acceleration, one will be a tangential, which is responsible for changing your speed, and another is centripetal. So I'll give you an example. Put it down. Others, keep your cams on. Copied. Next page. So let's see an example. Consider a vehicle starting from rest. Has a tangential acceleration a, which is constant. So let's see what happens exactly then. So we have a particle here and there's a vehicle here. So initially your speed was 0 and there is an acceleration. So this is your a tangential, which is a. Her radius is r. Put it up. So here, if you just observe at any time t, the speed will be like this. We can use the formula v is equal to u plus at. U is 0, so we get a into t. This is your tangential speed basically. Physical speed of the particle at any time t. Means if the particle has reached here, this guy will have a speed v. This is t0. Just a basic kinematics, we use u plus at. So the particle speed is increasing, it is going faster and faster and faster. Put this down. Then see. So what happens here? So after some time, if you look at this acceleration here, when the vehicle is here, there are two accelerations now, A tangential and A centripetal. What is A centripetal? We know A tangential is A, that is given. A centripetal is V square by R, and we know V is equal to AT. So you have A square T square by R. So the acceleration, right, if you observe, it's not constant, it's increasing with time. So the net acceleration will be somewhere in the middle. So unlike uniform circular motion where acceleration is always towards center, in non-uniform, the acceleration will be somewhere in the middle. So A net will be root over A tangential square plus A centripetal square. So that will be root over A square plus A square T square by R ka whole square. And if you take this angle as alpha, that is alpha is the angle between the net acceleration, we get tan alpha is A centripetal by A tangential. A centripetal is again A square T square by R by A. Put it up. So basically, see, there's nothing new. A tangential is given, from there you found the speed. Once you know the speed, what is centripetal? V square by R. So you find the speed from tangential, use that speed to find centripetal. Once you get both the accelerations, just square them and add them. There's a net acceleration. Copied. Now, if you just look at the profile, acceleration profile of the system, this is what you'll observe. Now, initially the particle, right? This is only A tangential, A centripetal was 0. When you're here, this was A tangential, this was A centripetal. This was A tangential, A centripetal is becoming bigger. Did you see? It is changing with time, na? More time, more A centripetal. That means the resultant will be like this. A tangential is constant, so A centripetal is even becoming bigger. So if you just draw the acceleration, net acceleration, this is what you'll observe. This is the net acceleration. Here it is like this. Here it is bigger. Here it is even bigger. So this is how the acceleration changes. So in a non-uniform circular motion, acceleration changes magnitude and direction. Suppose if you have taken a uniform circular motion, in that speed is constant, no? So there is only a centripetal, which is like this. Now here also direction is changing, but magnitude is constant. Magnitude is constant and direction of acceleration is changing. So this will be theoretical questions. In a uniform circular motion, acceleration is constant. True or false? Acceleration is constant. True or false? Wrong. Acceleration is a vector quantity. Direction change हो रहा है ना? Magnitude of acceleration is constant. True. Magnitude constant है. Acceleration constant नहीं है. So therefore acceleration changes, but magnitude is constant. Remember that. Put it down. So that's the acceleration profile. So there. So all this thing what we're doing today, right, will be there for the next Sunday exam. They're almost done. Actually, I'll show you two, three problems on this non-uniform circular motion, radius of curvature next class. We'll be done with the chapter. If it is done early, we'll start even new topic also, work power energy.
So can you show the previous page for a minute? After that.
Okay, so yeah, that's the last one for the day. So any doubts, anything that you have, please send me. If you got a lot of doubts, you can join at 11 o'clock, 11:5 after the second batch is over. If you got only 2 or 3 doubts, please ask now only. If you got a lot more, you can ask later. So yep. So with that, we're done with the session. So I'll see you next week. One second. Let's stop this.